Today we're going to talk about how we can count small things like atoms, molecules, and ions when we're dealing with chemical reactions. And we're going to be using a constant called Avogadro's constant and the concept of the mole. So remember that the atom is impossibly small. If we were to blow up every atom in a grapefruit to the size of a blueberry, the grapefruit would need to be the size of the Earth to hold that many atoms. So it's very clear that if we're going to talk about how many atoms are in a substance or how many atoms are in a grapefruit, that we are going to be working with an impossibly large number. So remember that when we think about a pure substance, so not a mixture like salt water, but just a pure substance, we can divide it up into elements and compounds. So these are the two categories of a pure substance. An element is an atom or a molecule, but it consists of only one type of element. So as an example, carbon is just C, right? It's just one carbon and they're all in this sample here. Sulfur makes a uh, ring with 8 atoms all connected. So these here are covalent bonds. So a molecule of sulfur, we would write that as S8. And a molecule, there are other compounds that have molecules as well, like the diatomic ones we've talked about, H2, O2, N2, and then the atoms. We've got carbon, and then a lot of the metals too, like iron or phosphorus is another one that makes molecules. So something like maybe copper. So atoms or molecules, but they're still a single element. And then we also have compounds. So one of the most ubiquitous compounds, water. So water is a compound because it has 2 hydrogen atoms and an oxygen atom. And so this would be a molecule. And then we have ionic compounds. And here sodium chloride is a good example. And you can kind of see how they're arranged in this lattice, this shape here. And we had a sodium donate an electron to the chlorine. So now we have a sodium ion, a chloride ion, and they are held together by the opposite charge. And so they're just attracted to each other and held together in this shape. So these are pure substances. They're all pure substances, but they all take different forms, from single atoms in a whole sample to covalently bound atoms making up a molecule of a single element to molecular compounds and ionic compounds. So now I want to talk about how we make compounds. So remember, these would be ions or molecules that have atoms of different elements. And I want to start off with the molecular compound of water. We're all pretty comfortable with water, and so I think this will illustrate the point quite nicely. So here, if we're going to make a single molecule of water, we're going to need 2 hydrogen atoms and 1 oxygen atom. If we want to make 2 water molecules, we will need 4 hydrogen atoms and 2 oxygen atoms. And this ratio here of 2 hydrogen atoms for every 1 oxygen atom to make that many molecules of water, this is always going to hold true. So let's say you wanted to make 100 million molecules of water, you would need 200 million atoms of hydrogen and 100 million atoms of oxygen. So if we know that water is always 2 hydrogen atoms to 1 oxygen atom, but we don't really have a way to visualize that. We cannot see individual atoms of hydrogen and individual atoms of oxygen joining to make individual molecules of water. However, we do have an analytical balance, and we could weigh certain masses of these compounds, and we could also weigh the molecules here. So we have to think about, how are we going to do that? Well, if we have a ratio of the number of hydrogen atoms to the number of oxygen atoms, we could do the same thing with mass. So hydrogen has a mass of 1.008. This is the average atomic mass based on the distribution of the various isotopes, remember. So if we were to think about a single atom of hydrogen, it has a mass of 1 because it is just a single proton. So we're going to say 1 AMU. And then oxygen, the most common isotope is oxygen-16, and so we would have 8 protons and 8 neutrons, and so we can say that is 16 AMU. So if hydrogen is 1 and oxygen is 16, that means that a single molecule of water has to have a mass of 18 AMU. So now we can look at the mass ratios here. So if oxygen is always going to be 16 out of 18 for the total mass. So 16 AMU of oxygen for every 18 AMU of H2O. And for hydrogen, we have 2 AMU of hydrogen per 18 AMU of H2O. So if you divide 16 by 18, you get 88.9%, which means that hydrogen will be 11.1%. So this mass ratio of 16 atomic mass units of oxygen to every 2 of hydrogen holds true no matter how many atoms of each you start with. So water is always going to be, no matter what mass of water you have, 88.9% of that mass is going to come from oxygen atoms, and 11.1% is going to come from hydrogen atoms, no matter the amount that you have. And so this has implications for all kinds of compounds. So we could look at sodium chloride. So sodium chloride forms when you have a single sodium ion and a single chloride ion, and they form NaCl. And if we look at our atomic masses of sodium and chlorine, and we would have to say, okay, we're going to use average ones, because if we were to work with a huge sample, we are going to use this mass here. So even though we're not talking about a single atom anymore, we're going to apply the same concept. So sodium has an atomic mass of 22.990. So we're going to use that one, 22.990, and that would be from sodium. And then chlorine, 35.453. And again, we have 2 common isotopes, and so we're going to, again, we're working with a large sample here. So don't worry about the units yet, but just know we're working with more than one. So the chlorine average, 35.453. So now we can take those 2 masses and figure out what the average mass of a sodium chloride ionic compound would be. So this gives us 58.443. So no matter what, no matter how many compounds you have, no matter what the mass is, no matter how many ion formula units you have, it's always going to have this ratio of 22.990 out of the 58.443, and that's for sodium, and then the 35.453 out of the 58.443 for chlorine. So if we divide these out, we would find that sodium makes up 39.3% of the mass of a sample of salt, of table salt, and chloride makes up 60.7%, which makes sense if you're comparing 35 to 22 out of 58. It makes sense that you're going to get about 60% for chlorine and about 40% for sodium. Okay, so now that we've thought about why we need ways to keep track of atoms and molecules that go beyond counting a single atom or a single molecule, I want to talk about units again. So we can't forget that we have to keep track of units all the time. And we can use those units to our advantage when we're trying to compare objects. So if we wanted to talk about a large volume of a liquid, we could talk about liters, and then we can also talk about milliliters. So 1 liter is always going to be 1,000 milliliters. We're pretty used to that one. We're also used to a dozen eggs is 12 eggs. So if you go to the grocery store and you get a typical dozen eggs, the carton for dozen eggs, you get 12 eggs. A ream of paper. So if you get one of those stacks of copy paper in the paper that's wrapped in like that shiny paper and you put it in the printer, that is 500 sheets. So if you order a ream of paper, you know that you're getting 500 sheets. A gross is 144 of something. And so a gross, actually, it comes from French and it means a large dozen. So it's a dozen dozens. So 12 times 12 is 144. So if you get a gross, you're getting 144. So we've seen this concept before, but remember how tiny atoms are. So if we are going to have a number that represents a certain amount of an atom or a molecule or an ion, it's going to be a big number. And we have one, and it is called the mole. And so a mole means that we have this many of that object. So a mole is simply a unit of measurement, and this is how many that is. So 6.022 times 10 to the 23rd is typically how it's abbreviated. It's how our textbook writes it. So it is a lot, right? So this is a huge number, and it sounds huge, and then you look at these samples here, and these are the samples that is a mole of that object, which means that in this powder right here, this mercury oxide powder, this beaker contains this many formula units of mercury 2 oxide. This beaker contains this many molecules of sucrose, which is table sugar. This one contains that many molecules of sulfur, S8, sodium chloride, which is table salt, copper, just copper metal. And so you can see how these are all different, right? So this is an element that is also a molecule. This is an element that is just a simple atom. This here and this here, these are ionic compounds. This is also a simple ionic compound, and then this is a more complex molecule. So it doesn't matter what the nature of the compound is, that it's just this many objects, and it could be ions, it could be molecules, it could be atoms, but these 1 mole samples of different elements and compounds kind of shows you why we need something like the mole. Because remember, hydrogen and oxygen have very different masses. Sodium and chlorine have very different masses. If you wanted the same amount of sodium and chlorine to combine to form a specific amount of sodium chloride, you couldn't just weigh them and do 5 grams of each, for example, because you would have a lot more sodium atoms than you would chlorine atoms, because the sodium has less mass. And so that's why we use this concept called the mole. So where does that number come from? Well, it's named for Avogadro, this Italian chemist from the 17 and 1800s. He did not discover the mole, but he was the first scientist to qualitatively describe what the mole might be in the same way that the old atomic theory was described as something must exist that is the smallest indivisible particle. And so Avogadro, he when people figured out what the mole was, or what this actual number was, when they solved this number, they named it after him. So this capital N lowercase this capital N subscript A stands for Avogadro's number, and we will be using this 6.022 times 10 to the 23rd. So this here is an exact number, so you don't really need to worry about sig figs when you're using this. You'll just want to use sig figs when you are talking about like how much of something you weighed out. So let's look at some molecular relationships and think about how many moles of each are in these compounds. So we're going to start off with C2H6O. So this is ethanol. And if you look at ethanol, you see that one molecule of C2H6O has 2 carbon atoms, 6 hydrogen atoms, and 1 oxygen atom. And if you have a mole, you would have 2 moles of carbon atoms, 6 moles of H atoms, and 1 mole of O atoms. And so you can set up a molecular relationship or a ratio and use this as a conversion factor. And so remember, these are conversion factors, not directives to solve a mathematical problem. So we've seen this before when we talked about converting between different units. And this is really all we're doing is we're converting between moles of a single atom and moles of a substance. And so we could do that with ethanol, and then we could also do it with something else. So let's think about glucose, for example. Glucose has the molecular formula of C6H12O6. And that means that for every molecule of glucose or every mole of glucose, you have 6 carbon atoms. Or, if you're going to do moles, 6 moles. So this would be a molecule and a mole. And then if we look here, we see that 12, that means that we're going to have 12 hydrogen atoms per molecule of glucose, which means that if we had 1 mole of glucose, we would have 12 moles of hydrogen. Finally, if we were to look at oxygen, and we have 1 molecule of glucose, we would once again have 6 O atoms, just like we do with the carbon, and we would have 6 moles of oxygen. So now you know how to count very tiny things like atoms, molecules, and ions.